And we're recording? Yes. Okay, fantastic question. So, read this little bit right here. Read this little bit right here. Just to read, it's been a week since I've seen you guys. Take a look at that little bit in need to light down a little bit. What's that? They have. Don't. Don't. Ooh. Oh. They have. Thank you. Bravo. So maybe the right one is some kind of a, like a sensory dimmer, which is clearly indicated by a caret pointing upward.
Obviously.
I'm being facetious. Very clear. I see a caret pointing upward, I think, now all the lights will dim according to the environment. No, this is great. Thank you for noticing that. That's fantastic. Okay, so Janelle, great question. Great question. We looked at a very, I think it was actually that function, f of x equals x squared, that we looked at in class. We said, you know, if x is 1, y is 1. If x is 2, y is 4. If x is 3, y is 9. And we did first differences that were all different, but then second differences were the same. And then we made essentially this claim, oh yeah, for quadratics, second differences are constant. And you were like, sweet, I'm getting hungry and I want to get lunch, so I don't care if it's true or not, let's just leave out of here. So what this essentially does is it asks you to be a little more rigorous in checking that. Is it actually true for all quadratics? And so what I'm asking you to do here is do a little bit general. And the generalization of it is, instead of using the function f of x equals x squared, which is one very specific quadratic, I want you to use f of x equals ax squared plus bx plus c. Does that look familiar?
Yes.
It's exactly, when you run quadrag in your TI, it puts that at the top. Y equals ax squared plus bx plus c, because that's the general form. Well, I'm calling it general. I don't know what it's actually called. But that's the most general form of a quadratic I can think of. A, B, and C are the coefficients. Let me ask you a quick question before we move on. This is a quadratic, which means it fits in this form. What are A, B, and C for that one?
A, B, and C.
Yeah, A, B, and C all have numerical values in that one up there. What's A? If f of x equals x squared, let's put this up for a second. Okay, if f of x, there you go, equals x squared, and I know that the general form of a quadratic is f of x equals ax squared plus bx plus c, what's A? This is Ben, right?
1.
The A's 1. You don't see anything in front, which means multiplied by 1.
Yeah.
So your A value is 1. How about your B and your C values?
0, 0.
What are those? I don't see anything x. There's no like plus 2x or minus 3x. So B's got to be 0. And C's not there. There's no constant, so C's got to be 0 as well. Now the reason I bring this up is you probably remember that from back in the day. Back in the day! When you ran like the quadratic formula, you would have to extract those exponents and stick them into the quadratic form. Excuse me, not the exponents, the coefficients, and stick those into the formula and generate your roots. Go ahead, Ben.
But we know that minus bx plus c equals 0, but it doesn't mean b equals 0 and c equals 0.
What you're saying is minus bx plus c equals 0. You're implying that x has a variable value. There is no x presence in the function f of x equals x squared. F of x equals x squared, if you graph it, looks like this. It's got a vertex right at the origin. If you start putting an x, a linear term on that, it's going to start moving this thing around from its position. And if the plus c is on there, it's going to move it up or down from that position. So there is no linear. This is called the quadratic portion, the linear portion, and the constant portion. There are no linear or constant portions on that function. Does that ish make sense? Good. Very, very good point. Very good point. I saw another hand go up. I thought over here. No.
No.
You guys good?
Yeah.
You're good. All right. So basically, this right here is a very specific quadratic function of which this is the general part. What I want you guys to do is, I want you to set up a little bit of an analytical table. Thank you, Janelle, that's a great question. I want to set up a little bit of an analytical table and look at this, which looks ridiculous, looks terrifying. We're going to be less terrified today when we're done. We're going to be less, I promise you this. I promise you this, we're going to be less terrified. So let's do E5, and what the hell, we'll do E6 as well. And then I guarantee once you do E5 and E6, E7 will be like, oh yeah, I'm on this. I totally got this. Okay? So if we're going to have to figure out, what, I'm going to write this on the board. I'm going to turn the screen, turn the projector off. We're going to need f of x. We're going to need f of x plus 1. And we're going to need f of x plus 2. Okay, so let's mute the screen. There we go. And we know we're using this as a function. Okay. So let's see what each of these means. I know f of x is ax squared plus bx plus c. I know that. I'm going to move this one down. More space than that. Make sure we can see this too. Ish. There. What does this mean, f of x plus 1? X plus 1. Actually, we're using function notation. It looks like that. It looks like f times x plus 1. What it means is you're sticking this into the function. So what this means in words is stick, I'll put it in quotes, stick x plus 1 in wherever, somebody just said it, wherever you see an x. Wherever you see x. And that's what it means in words. Up here, you stick x in wherever you see x. Well, that's kind of silly. It's already there, so you're done. This means stick x plus 1 in, x plus 1 in wherever you see x. That's a lot of weird consonants. Sorry. So let's do it. Let's do it. I see an A. I see an x. I want to change x to x plus 1. So it's going to look like that, x plus 1 the quantity squared. Plus, I see a b, yes. I see an x. That becomes an x plus 1. Notice how I'm using parentheses. Notice how I'm using parentheses. Very, very important. Because you've got to make sure you're actually substituting with correct order of operations the entire value. Then I see a c, which is over here. Coolio so far? Ish. Getting there. Make peace with it. Coffee helps.
Make peace with it.
Make peace with it. Coffee definitely helps. You know what? What the hell? Let's do f of x plus 2 while we're here. Let's do f of x plus 2 while we're here. Because I think you guys are going to see what this is going to look like now. A times x plus 2 to the quantity squared plus b x plus 2 plus fan-friggin-tastic. So that's what the actual, what you're doing in abstract terms right now, friends, is the exact same things we did in concrete terms on, I think it was Thursday. We don't need this right now. On Thursday.
Oh, with the little second.
Yes! We're setting it up generally, Tiff. Yes, that's a great connection. In class on Thursday, we were using this function right here. And we set up a table, x, and we may have called it f of x, we may have called it y, I don't remember.
Y.
We called it y?
Yeah, we did.
Yeah, we
Totally
call it
fine.
y.
We call it y. Same thing, f of x, y, it's all the same thing. But it's totally, we'll call it y. And then I went 1, 2, 3, 4, and 5. And then we created the y values, which were 1, 4, 9, 16, and 20. I think we went further than that too.
Yeah,
But do you see how each one of these x's is increasing by 1? Each one of these x's is increasing by 1. So what you're doing is, you're being extraordinarily general in your attack, and you're trying to see why what we saw on Thursday will work in general. That's the beauty of it. That's the beauty of it. So that's all you're doing is you're generalizing the argument. Instead of saying, how many of you have been told something like this? Well, I know smoking's great for you, because my uncle's been smoking 2 packs a day for 45 years, and he's still alive running marathons. I mean, you've heard, it's a ridiculous example, but you've heard something like that. It works in one case for one person, so therefore it has to be true. You know what you say? You say, no, it works for that one person. It doesn't prove anything. That's one person. What you show it to me that it works in general, on average. That's what you're doing. You're showing something holds in general on average. Actually, not even on average, in general, because it's pure mathematics, not statistics. Cool so far? All right, let's do E5, per Janelle's requests. E5 says we have to do, correct me if I'm wrong on this one, f of x plus 1 minus f of x.
That's right.
That's what we got to do right now. So we've got to take what f of x plus 1 is equal to, and from it remove, let's move this a little bit this way, remove f of x. Good. So f of x plus 1 is this stuff here. So this is a times the quantity x plus 1 squared plus b times the quantity x plus 1 plus c. That right there, I'm going to use a little bit of color here to kind of highlight stuff. That whole thing is f of x plus 1. That's called a substitution. That is probably the most important mathematical skill you will ever learn, or you ever have learned in your lives, is being able to substitute equal quantities for something else. I hear the last time we did it in class was that tree cross-section problem, and I think I pissed 92.5% of you off that day. Yes, you did. Yes, you did, Sean. I apologize.
Sorry.
Because it's one of the most important tools in mathematics, given a substitute. So all I did was I took this and replaced it with this because of that beautiful symbol that's right there, equals. I'm going to do the same thing for f of x.
Okay.
Minus, now I want to intentionally leave something out for a moment and put it back in later. Minus f of x. F of x is ax squared plus bx plus c. I did forget something though. Because this now, this little bit here, is equal to this. But I forgot some, you got it, Kurt. I forgot the grouping symbols of that. I have to make sure, if I'm subtracting f of x, I have to subtract all of it. And if I don't put those parentheses, it's only going to subtract the ax squared part. It's going to add the bx and add the c. And we're not going to get Ben's negative bx minus c that we need to get into the computation. That's an old algebra trick. Sorry if it's a bastard trick. But unfortunately, we have to abide by it because it's the mathematics of equality and subtraction in this case. That equals something. Our job, figure out what. Our job is to figure out what. So now, let's get rid of as many parentheses as we can. That's our job now. Let's get rid of some parentheses. Who wants to take first shot? Get rid of some parentheses, including the ones I just added in. You can get rid of those too if you want. Let me hear some ideas. I'm hearing a voice from somewhere. It sounds confident, mathematically correct.
No, not yet.
No, not yet. We're getting there. We're getting there.
I'm thinking out loud.
Thinking out loud. Tell me your name again, my friend.
Kathy.
Kathy and Janaea. Go ahead.
I don't know.
No? Okay. You don't have to.
Put the A in the first parenthesis.
Ah, love it. Okay, we'll get the A. Tiff, what do you think back there?
Put the a to the x because it's squared.
We're hit.
That crosses that x squared out. X squared.
I love this. I have one caution. What has to happen first?
Parentheses.
We have to get rid of parentheses first.
Parentheses first.
But please excuse, I hate this. By the way, YouTube, I hate this. But everybody learns it this way. Please excuse my dear Aunt Sally.
That's what we remember. Love it.
I know, but well, okay.
Okay.
All right, it'll work fine in this case. Never mind. It works fine in this
Better.
case. Let's use it. Let's get rid of some parentheses. We can't do that, my friend, because it's not equal to anything. It's an expression. We've got to get rid of the parentheses first before we do any multiplications. So let's work through them. First of all, this one, let's get rid of these parentheses on the end here. The way we do that is we simply drop the parentheses and make everything inside the opposite of what it was before. That's the definition of subtraction. The definition of subtraction is adding the opposites. That's what we just did. We're adding the opposites. See this plus C? That plus C is still a plus C. He's still there. So Tiffany, I'm starting to see your cool cancellation happening already. Very nice, my friend. Hold tight on that one. How about this guy right here? This bx plus 1. What should we do here? That's going to be plus bx plus b. That's going to be right there, right? S plus bx plus b. And then here we're going to have, this is where it gets a little bit challenging algebraically, mathematically. You're going to have an A, right? A. What's x plus 1 the quantity squared? Let's come down here. X plus 1 the quantity squared. What is x plus 1 the quantity squared? This is worth a sub-trip down here. It's tempting to say x squared plus 1. But, Tiffany, say it nice and loud. It's x plus 1 times x plus 1. And when you look at it that way, you realize there's two extra x's that you might forget. So it's actually going to be x squared, x times x, plus x plus x, which is plus 2x plus 1. That's what you have to kind of deal with. So it's x squared plus 2x plus 1. I want to scooch this over a little bit. So it's x squared plus 2x plus 1 plus everything else that's in line here. So when you FOIL, it's called foiling if I remember correctly from back in the day. When you FOIL out x plus 1, it results in that. And that's easy to forget. That's extraordinarily easy to forget from back in the day because it's just one of those algebraic skills that might never make sense to you back in the day. It might kind of throw you for a loop. May I offer you a geometric explanation of why that works? Some of you are still sitting there like, I still don't know. I still just memorized. It's x squared plus... Let me try some geometry to explain that. We're going to take a little pause here and go off to the side. So when you see something like x squared, you know whatever the number is, you're going to multiply by itself, x squared. So a way to think about that is thinking of it as a square where both sides are size x. And then you guys have been hopefully playing with squares your entire life, figuring out how much paint to buy for a wall or something like that, square feet. Or how much if you want to make your garden depth 6 inches of mulch, how many square yards of mulch you need, yard times yard. So hopefully you got that idea. So what happens if x squared becomes x plus 1 squared? What would that square look like? What would that square look like? Well, it would look like, you would have x like here, right? You'd have that much x, but then you'd have how much more on each side? You'd have 1 more on each side. I don't know how big 1 is. I'll just make 1 like arbitrarily like that big. And it would also be this big on this side, right? Same size. And then it would come down like this and like this. So clearly, this is 1, and this is 1 here. So you've got x, which takes you to here, and which takes you to here. And then you've got this extra 1, and I have no idea how big x is, and I'm just arbitrarily calling it this big. There's 1 there. Now do you see, if I was to break this down into geometry, is this guy right here, does that ring a bell to you? That's this guy, isn't it? That's your little x squared. But aren't there other pieces in this picture besides that x squared? There are 3 other pieces. There's this piece over here, there's this piece down here, and there's this piece right here. What's this piece right here as an area? Well, what kind of shape is it, first of all?
Square.
It's a square, isn't it?
Yeah.
If anybody said rectangle, you're correct too. It is definitely a rectangle, but more specifically, it's a square because it's got equal sides. What are the lengths of the sides on this thing? Go ahead, be brave. We got 1 and 1, which means it has an area of 1. So here's the problem. When you say this equals x squared plus 1, then you're saying that this is only made up of this piece and this piece. But doesn't it also have this piece and this piece in there? And what are these pieces over here? Well, they're 1 by what?
By x.
By x. So what's the area of this piece right here?
1 by x.
Just x. How about this one up here? Isn't that also x as well? So when you collect all the individual areas, you get x squared plus x plus 1, which is x squared plus 2x's plus 1. And each one of those pieces is part of the FOIL. When you learned FOIL back in the day, the x plus 1, the quantity squared, you learned it as x plus 1 times x plus 1. And that's what you're looking at right here. This x plus 1 is one of the sides. That x plus 1 is another one of the sides. And then you learn the foiling. You said, okay, we got to do this one times that one, and then this one times that one, and then this one times that one, and then, which one did I forget? This one times that one. And you may have sat there and been like, what the hell? Why do I have to do those 4? That's why. That's why you have to do it, because you have to stretch the square that you started with of just x into a bigger square, x plus 1 by x plus 1. And when you do that, you pick up some extra pieces. So just in case you needed another way of thinking about why x plus 1, the quantity squared, is x squared plus 2x plus 1. This is a geometric look. And this will work for any numbers, just so you know. It'll work for x plus y. It'll work for x plus 3. It gets a little trickier in all sorts of like x minus 3. You have to get kind of clever on how you set that kind of stuff up. But just in case, it's one of those things that can throw students, especially algebra students who tended to memorize their way through something. That's just another way of looking at it. Okay, back to this. We're back over here now. What do we do next? We got to get rid of the parentheses, right? So we got to get rid of ax squared. So that's ax squared. 2ax a. Yeah, so far? bx b c minus ax squared minus bx minus c. It's getting a little nausea-inducing. But thankfully, some of this stuff will cancel out, right? Some of this stuff will go away. Some of this stuff is going to go away. What goes away in particular? It looks like, yeah, that guy over there, that guy right there, this guy here, yes? And the C, and that guy right there. And I think, how about that A? Is that A stay? A stays, 2ax stays? B stays? Okay, I think we're there. We've got 2ax plus a plus b. 2ax plus a plus b. Now, that looks a little bit strange, probably. But what you're looking at right there, I want to compare and contrast that back to what we did in class with an actual equation, with numbers, not with variables, but with values. So, where can I put this? I want to make sure it's visible when you're looking at this later. Let's put this down. Okay, so in class, we had, this is just like in class, just a compare and contrast. We did x and y, and we had 1, 2, and 3, and 4, and 5, and it was 1, 4, and 9, and 16, and 25. You just did f of x plus 1 minus f of x. So essentially what you did was, you did a y value minus a previous y value. A y value minus a y value gotten from an x value that's 1 less. So you took like 9 minus 4 and got 5 right there. Or it was 16 minus 9 when you got 7. Or it was 25 minus 16 when you got 9. It doesn't matter which one it is. You started with a y value, which is what f of x is. And you subtracted the previous y value, which was what f of x is. So f of x plus 1 is whatever y value it is that you decide to start from. And you subtract off the previous y value. So that's what that equals. It just equals, in general, what that particular y value is for that value of x, in general. So that's your E5. E6 would have you do the exact same thing, but you would subtract this one minus this one, instead of this one minus this one. Everyone with me so far? So you're doing this guy minus this guy, instead of this guy minus that guy. See what I'm getting at? Okay, fair enough, fair enough. Shall we? You're starting to get that look. You're starting to get that look. It's just more algebra. It's definitely algebra. That's the part that's a little bit, I mean, it's tedious, but it's no more algebra than we just did. It's just that we just have to do x plus 2 and x plus 1. Tiff, go ahead. No, go ahead.
So I understand this like once you start talking about it, but then once you talk about like the x, y, the minus all that over there, the table.
Yes? It's the same thing. It's just that this is the general form of it, and that was a specific when we did it in class. So in other words, when you hear f of x from your previous math classes that you guys have taken, Math 95 in particular, what does f of x mean? Right. What variable do you think of when you think of f of x? It's y, right? So what this is a y value from this x value minus a y value from this x value. And this x value is 1 bigger than that x value. So when we did it in class, we had x values that were always 1 bigger. 1 bigger is 2, 1 bigger is 3, 1 bigger is 4. So x plus 1 is any one of them on there. X is the next one below. So if x plus 1 is 5, x is 4. If x plus 1 was 4, x was 3. If x plus 1 was 3, x is 2, and so forth. It doesn't matter which one you use. This works for all of them, including the ones we didn't do in class. That's the power of this. You're actually getting a generalization. The f of x plus 1 is just the y value that goes with whatever x value that was. Is that fair, my friend? And f of x is just the y value that goes with whatever x was. And subtracting them is just like we did in class when we did one minus the other. It's just a generalization of everything we did on whatever it was last Tuesday. Please.
So, I mean, go a little bit more with that in class.
Yeah.
Do E5 with those numbers.
Oh, great point, great point. So let's see how E5 plays out with the function from class. Okay, fantastic. First of all, we have to pick some numbers that we're going to use. Which one do you want to use? Do you want to use 5 and 4?
I like 5 and 4.
5 and 4. We're going to use 5 and 4. So here's general. Let's go to specific. All right, let me swing the camera over there so we can see it on the side. Can I erase the square over there? We're done with that, I guess. All right. Now I got to go back to the original function. Original function in class.